These are the strangest problems in math. Despite this, they each have their own merits that are worth learning. Today we're going to be discussing the most random problems that do not really fall into any category, but they're still cool, and let's start off with a simple example from Math Counts. A restaurant sells drinks, three sizes of drinks: small for $1.20, medium for $1.30, and large for $1.80. Each person at the table of 10 ordered one drink for a total cost of $14.90 before sales tax. How many people ordered a large drink? So this is a classic type of problem where the idea is to find out this, you want to assume everyone orders a small drink first. So what happens if everybody orders a small drink? There's 10 people, table of 10. So if everybody orders a small drink, then the total cost would be $12. Now this is obviously not right. It's $14.90. So $12 is the cost if everyone orders a small drink. But what if that's obviously not the case? So how much extra money do we need? We need an extra $2.90. Okay, so how are we going to get this $2.90, the extra that we need? This is extra we need from small. The idea is medium drinks offer an extra $0.10. Large drinks offer an extra $0.60. And this is all compared to that baseline $1.20 for the small drink. So essentially what that means now is both of these extras combined, the extras for the medium and larges combined must form $2.90. Okay, but the thing is there's only 10 drinks total, right? So we somehow have to use 10 cents and 60 cents to form $2.90, but there can't be more than 10 medium drinks, and there also can't be more than 10 large drinks, because we only have 10 total drinks, right? And also there can't be more than 10 total medium and large drinks as well. So the number of total medium and large drinks, let's write this here. Total medium plus large less than 10. Cool. So $2.90, let's look at the possibilities. One possibility is we have 29 medium drinks. 29 is way bigger than 10. No. Another possibility, one large, and that gives us an extra 60 cents, and then 23 medium drinks. That also doesn't work. Now we can keep going up and up, but I think now it's clear that we need to have a decent amount of large drinks, or else we're going to need way too many medium drinks, way more than 10. So now instead, let's look at the maximum number of large drinks that are possible. Let's say we have 4 large drinks. That gives us an extra $2.40. And now, to get the last 50 cents to get $2.90, we need 5 medium drinks. And that gives us the extra 50 cents we needed. Aha! $2.40 plus 50 cents, that gives us $2.90. And the total number of medium and large drinks is 9, which is less than 10. And if there's 10 total drinks, that means there must be one small drink, right? So the answer is just going to be 4. And just to make sure we're not making a mistake, let's check. 4 large times 180, that's 720. 5 medium, 650. 1 small, 120. We add this all up, we do indeed get $14.90, so we did not make a mistake, luckily. And 4 people ordered a large drink. Okay, now we're ready to move on to the next problem. Before that, let's just summarize our steps that we did for this problem. So the key idea was looking at the extra money we needed. And this is a standard problem. If you've ever heard of the chicken rabbit problem or whatever, where it's like there's this many heads and this many legs, how many chickens and how many rabbits are there? It's the same idea. Assume all of them are the ones with less legs on them, and then look at the extras. Okay, next problem. Math count. Another math counts one. John inserts some number of parentheses into the expression shown to create a valid mathematical expression. What is the smallest possible integer value of John's expression? Integer, okay, this is interesting. We can put parentheses however we like there. You can put some here, you can put some here. The point is, parentheses, the key idea is, let's say we do something like that. Now, because we do divided by 2 over 3, that's the same thing as flipping these two terms in the parentheses. So 3 divided by 2. So that means that the key idea here is that we want to have every number from 1 to 10 here can either be multiplied by or divided by. And the reason this is true is because 2 divided by signs, let's say we have divided by and then 2, and then another divided by 3. 2 divided by signs make a times sign. So this would essentially be equivalent to divided by 2 times 3. So essentially what that means is that this is the same thing as being able to just say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Insert multiply and divide signs however you like in this expression. Because we can place parentheses wherever we like, and 2 divided by signs becomes a times sign here. Like if we have divided by 6, divided by 7, divided by 8, these signs would both become times signs. Because we're dividing a divide sign. So that essentially allows us to form a times or divided by sign for pretty much everything, for almost all the numbers in this expression. It actually turns out that the only one that this won't work for is 2, because 2, there's only one divided by sign in front of it. But everything else, like 3, you can get, as you can see here, times. Everything 4 can be times, 5 can be times, and all the other ones can be times. So other than 2, which is forced to be a divided by sign, everything else can either be times or divided by. And now it's asking, what is the smallest possible integer value for this expression? Okay, so how should we do that? Okay, so the key idea here is that 7 is a prime, 5 is a prime, 3 is a prime, and 2 is a prime. 5 and the prime 5 appears 2 times. So we're essentially multiplying some numbers, dividing some numbers. We want stuff to cancel. Make stuff cancel. How do we do that? Well, we've got a 5 here, a 10 here. So what we can do is say, let's do times for one of them and divided by for one of the others, so that the factor of 5s cancel out. Okay, now let's look at the factor of 3. Which of these numbers are divisible by 3? 3, 6, and 9. 3 and 6 each have one factor of 3, 9 has 2. So what we can do is say times 3 times 6 divided by 9. And that way, we're left with no factors of 3. So no factors of 5, no factors of 3. Now, what about 2? Well, this must be divided by 2, right? We've already got 2. We've got a factor of 2 from here, which is 4 already times. We've got a divided by 2 from here. We've got a divided by 2 from here. And these two numbers we don't know yet. So far we've got 2 divided by 2s and 1 2. So far we have divided by 2. And we want to make it as close as possible to nothing. We want to make it ideally 1, if we could do that. We would ideally like to make the number no factors of 2 as well, to make it as small as possible. Now, is that possible? We've got an 8 left and a 4 left. where we can assign a times and a divided by sign. Look here, we've got a divided by 2 sign, so it would be great if we could have times 2 from the 4 and the 8. And that's indeed possible. Times 8 divided by 4, 8 divided by 4, that's 2. So this would be times 8 divided by 4, and if you do 8 divided by 2 times 2 divided by 4 divided by 2, that's equal to 1. So no factors of 2 as well. No factors of 2 as well. That is possible indeed. Now the question becomes 7. We haven't looked at that yet. The thing about 7 is it's the only number without another. There's only one number that's a multiple of 7. And we can't make that divided by, because then we'd be having a fraction 1/7. And that's, clearly says integer. So we have to make it times 7, so we're kind of forced to. So there's one factor of 7. So then what's our answer? It's just going to be 7. Remember, there's no other prime factors from 1 to 10. So our answer is just simply going to be 7. To review everything so far, basically what we had to do was place times and multiply signs for each, and look at each of the prime factors separately. And then, essentially, we just looked at a possible configuration where maybe we could get no factors of 5, no factors of 3, and no factors of 2, and we did find one. But remember, the idea was parentheses means that you can have times and divided by wherever you'd like, pretty much, other than here, right? Because, for example, let's say you wanted 1 divided by 2 times 3 times 4. Then you would just do 1 divided by 2 divided by 3 divided by 4, like that. Or if you wanted 1 divided by 2 times 3 divided by 4, you would just do 1 divided by 2, and then 2 divided by 3, and then inside here divided by 4. The point is, like, the number of parentheses will eventually cancel out to form the expression that we want it to form. Okay. We're ready to move on, and you can find this interesting example about some cool prime factor stuff in the book Free Mastering AMC 8 book, link in the description of the video. Let's move on to this AMC 8 problem. When a positive integer n is fed into the machine, the output number is calculated according to the rule shown below. N. If n is even, divide by 2. If it's odd, multiply by 3 and add 1. Now this is actually an interesting story. This problem is based off the Collatz conjecture. And this is actually a famously known unsolved problem. Nobody in the whole world is able to solve it, so it's pretty hard, as you might guess. But this problem is the, of course, easier version based on it. And it's actually very cool. There's a cool property about Collatz conjecture that's actually shown here, and I'll talk about it later, maybe. Okay, so basically, for example, we're starting with 7, we get 7, then 22, then 11, then 34, then 17, then 52, then 26. Right? We're just following these rules. When the same 6-step process is applied to a different starting value of n, the final output is 1. Find the sum of all such integers n. Okay, so the key to this problem is work backward. Because we know the final value, it's going to be much easier just to look at the possibilities for each position. So we're just going to zoom in here. We know our rules, right? Odd times 3 plus 1, even divided by 2. So what are the different ways to form 1? Well, we can either have, if the number here was an odd number, then we could do 0 times 3 plus 1. If the number here was even, it would just be 2. But the key thing here is no number in the sequence can ever be 0. Why? We're starting with a positive integer. And it says here, positive integer n. And if we're starting with the positive integer, there's no way to go from a positive integer to 0. And by dividing by 2, there's no way to go from a positive integer to 0. And neither is a way to go from a positive integer to 0 by doing times 3 plus 1, because there's literally a plus 1 term. And same thing for divided by 2. when we're dividing a positive integer by 2, it's going to stay positive. So this is not possible. So just 2 is the only possibility right here. Okay. Now, what about this position? Next one here. Now 2. Now, there's two cases again. If this value was odd, then we could do, well, then we would have, if something 3x plus 1 equals 2, where x is some odd number, right? But does this have a valid solution? No, it has to be integers, right? So this won't work. So that means what must happen is that this must be a 4 over here. We must divide by 2. Because there's no way to do times 3 plus 1 to get to 2. Okay, now what about here? Now here we actually have two possibilities. Now if the value over here was odd, then we could just do times 3 plus 1. Right? 1 times 3 plus 1 equals 4. So this value could be 1. Right? If that does work, because 1 is odd, 1 times 3 plus 1 is 4. The other possibility is if this number was even, we divide by 2 to get 4. And of course, 8 works in that case. So our two possibilities are 1 or 8. Okay, now what? Now, let's take these two cases separately, and I'm actually going to write it here separately now, so you can see stuff clearly. 1, 2, 3, 1, 2, 3, 4, 2, 1, and then now we found two possibilities here, right? 8 or 1. So if the previous value was 1, we already discovered that if the next value is 1, the previous value is forced to be 2. We already discovered that. Because over here we discovered that times 3 plus 1 would mean the previous value is 0, but that's not possible. So we already discovered that if the last value is 1, the previous value must be 2. Now what if the previous value is 8? Then the new value can be, if it was even, it could be 16 divided by 2. And if it was odd, we have 3x plus 1 equals 8, or 3x equals 7. That's not possible, not for any integer solutions. So the only possibility is 16. The only possibility for the previous number, if this number is 8, is 16. Because you can't do times 3 plus 1 to get 8. Okay, now what about for this value here? There's only two cases, so we just look at them both. Did I have enough blanks? 1, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, we do have enough blanks. Okay, so what about here? What are the different possibilities? Of course, if it was 16, it could be, move this out of the way. There's two possibilities for 16. If the previous number was even, you could just have 32. 32 divided by 2 is 16. If the previous number was odd, 3 times the previous number, x plus 1 equals 16. Oh, so the previous number can be 5. Now what if it's 2 here? Like we discussed earlier, if a number is 2, the previous number must be 4. So this value is forced to be 4 in this case. And now finally for the last value, n. Remember, we had n goes to one of, so n can go to one of these three values. But to find n itself, we need to again consider a few cases. So 4. What values can come before 4? It can be 8 or 1, like we already discovered, because if it's even, 8 divided by 2 is 4. If it's odd, 1 times 3 plus 1 gives 4. So 8 and 1 are two possible values of n. Now if it's 5 or 32, then we have some possibilities as well. So if it's 32, of course we can just have 64. and then just do 64 divided by 2. And also, times 3 plus 1, if we have something like 3x plus 1 equals 32, 3x equals 31, this isn't possible. So the only possibility for n, if the previous value was 32, is 64. Now, what if the previous value is 5? Now, what if this value is 5? Then the previous value, if the previous value is even, it can just be 10, because 10 divided by 2 is 5. If the previous value is odd, we have 3 times that number, plus 1 equals 5, which means 3 times the number equals 4. Not possible for any integers, so there's no possibility here. And that's it. These are the only possibilities that we have. So now what we can do is just add them up. 64 plus 10 plus 8 plus 1. And that is equal to 83, our answer. So the key idea here was just looking at this and working backwards. 1, 2, 4, and then we discovered 2 possibilities. And then for each possibility, we just considered 2 cases. If the previous value was odd or even, not all the times did both of them work, but sometimes they did. And we ended up getting 4 final values that worked and adding them up. And interesting, notice here 4, 2, 1, 4, 2, 1. Now this is actually based off the Collatz conjecture, which states that if you start with a number and apply the sequence of moves, it will eventually reach 4, 2, 1, and then it will just keep cycling. 4, 2, 1, 4, 2, 1. Notice how it kind of cycles here as well. 4, 2, 1, then back to 4, then 2, then 1, then back to 4, 2, 1, and that will keep happening forever. And the Collatz conjecture basically says that that will happen for all numbers, except no one has proved or disproved it yet, so it remains a mystery. You can find another good video on another channel, Veritasium, which explains the Collatz conjecture in more detail if you're interested, but this is a really cool paradox. Maybe you'll be the person to solve it one day. Anyways, thanks for watching. See you in the next video. You can click that right there. We'll discuss geometry.